So the previous lectures were mostly about the data, the communication networks, right? Where we had the switching network and then the uh, broadcast network, and then the switching network we covered um, circuit switching and then packet switching. Okay. S- So on that basis, I'm just trying to recap what was covered last previous lecture. It's lecture 4. And so moving on from that, we want to cover um, some of the key um, some of the more or less the some of the significant attributes that relates to the physical layer, especially when it comes to signal and data or data and signaling. We'll look at some of the uh, calculations. We want to look at how digital signals and analog transmissions are handled. We also want to look at the multiplexing implementations within uh, within the physical layer of the OSI model. Okay, so more or less this lecture is just going to be covering the signaling um, aspects of data communication and networks. Okay, so first to start off, we want to talk more about signals. Signals are quite essential. That's very important at the physical layer. I mean, in all uh, specification, the physical layer revolves around signaling because that's where uh, the, the the bit sequence are more or less about to leave the particular network device onto a different network device, and the medium through which the transmission takes place. Uh, the, the information has to be converted to a signal form before the signal can actually transmit it. So this is where you look at digital signaling and analog signaling within the transmission part. Okay, so signaling first. All right, and then we'll look at in the more of the 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 layering stacks at the physical layer coming up from the data link layer. We'll look at some of these key uh, protocol services that needs to be um, looked at or that needs to be observed before or to guarantee a reliable information transmission at the physical layer when uh, signals when signals about to leave the system into a medium. Okay, so issues like or concerns that relates to bit signal transformation, um, bit synchronization, switching elements, bit controls, bit rate controls, and multiplexing are some of the key things that we want to cover at this particular layer here. So we want to go in depth in some of these things, how uh, they go about with managing and handling bits before they get handed over to the medium, either as an analog signal or as a digital signal, en route to a particular node, or ultimately its final destination. So that's what really we want to cover in this part of the lecture. Okay, so we started with signals, and now we're going to go through digital transmissions, analog. So obviously, in the signaling, these are some of the key things that you'd be looking at. One of them is digital transmission, analog transmission, multiplexing, and then obviously the transmission medium that's helping with the transmission of some of these signals, or helping with the carrying of these signals from a source node to a destination node. Okay, so signals in general, when it comes to data, it can be either grouped into two parts or two forms, and one is either analog or digital. So data can be either analog or digital. And the term analog data refers to information that is continuous. So when you're looking at information or signaling of data at the analog level, we're more or less looking at a stream of waves going through a medium at a continuous rate. Okay. Whereas digital data actually refers to information that has a discrete state. So it can have either a high or a low state, which is either on which is usually represented as either binaries or as on and off in terms of voltage level transmission, or voltage pulse transmission. So that's where we derive your digital, or more or less the binary sequence of digital data from, because it can only has discrete states, which can either be either 1 or 0, or in other words, it's either on or off. On when it's 1, and then off when it's off is 0. So that's what forms your binary digits within data data transmission. Okay, analog generally also takes on continuous values. Um, they also do take continuous values, but generally it's digital data that takes on discrete values. Okay, so keep those two things in mind. Um, uh, Analog data are usually referred to as information that is continuous. They do also have values, but the values are going to be represented in a continuous form. Okay, so every signal that you transmit, whether it's analog or digital, it would have some kind of value. But depending on if it is analog or digital, will determine what kind of value it will take. So that's what we said earlier on, that analog data taking its value is going to be more or less related to continuous uh, uh, forms in terms of value. So analog data takes so analog data takes on continuous values, and digital data takes on discrete values. So data can be analog or digital, and the term analog data refers to information that is continuous. So which means the value we take will be what? Continuous values. And then when it comes to the digital part, since it's more or less related information that is discrete, and the values it would also take on will be discrete values. Okay. So to be transmitted, for data to be transmitted either in an analog or digital form, uh, it needs a medium, and the medium is usually in the medium is usually within a given uh, uh, a given transmission physical form, which could either be via copper medium, a copper wire, or it could be just over an airwave or even through a fiber optic cable. But generally, data being transmitted um, can be transformed into electromagnetic signals. Okay, so data that's been transmitted can be transformed into electromagnetic signals. And when data takes on either analog or digital states, it just means that you're going to have these representation of their various states as well as values that goes with it. So for notes wise, these are some of the things that you want to just summarize it to. So you can say to be transmitted, for this to be transmitted, it must transform into electromagnetic signals. And data can either be analog or digital. And when it's in analog form, it's continuous and takes up continuous value. But when it's in digital form, it takes up discrete states and as well as discrete values. Okay. Okay. Um, Signal can also be, which is the same thing, analog or digital. Okay. And signal and analog signals do have infinite number of values in a range. So if we talk about analog data being continuous, then obviously it will take continuous values. So if we do have analog signals, it means its values will be continuous in an infinite range. Okay, so the values it will take on will be an infinite range. Okay, but on the other hand, when it comes to the digital signal, which can only have limited number of values, in this case either 0, 1, or on and off states, because of the fact that their voltage pulse is being switched on and off. So look at that. So if you notice, we are talking about um, data as analog or digital, and we're also talking about signal as analog or digital. And when data takes on analog form, it would have uh, a district, sorry, it would have a continuous state. Okay, when data takes on an analog form, or when data is analog, or when we say analog data, we're going to be talking about data that's having a continuous state or continuous form. So it means that from the at the signaling port or signaling level, if a signal also takes on the analog state, uh, its continuous flow would also be well established in more or less an infinite form in terms of value. Okay, and then when it's digital, which will be much more of a discrete state, and taking on discrete values. So if signal was in a digital form, then it also have that discreteness uh, will apply to its values, or it will apply to its states. So in that case, signals that are at the digital level would definitely have limited number of values that it can take on. Okay, since digital data um, happens to have discrete values, signaling at a digital level would definitely take on or must take on a limited value in terms of its representation. That's where you have your zeros and ones, as I mentioned. Yep. So that's where you here. So you have data having a discrete states and taking on discrete values. And those for signal representation, you would have signal being either analog or digital. When it comes to analog, it would have infinite number of ranges because of the fact that it continues. But whereas the digital signal would only have a limited number of values. In this case, it would be either 0 or 1. So here are examples of what analogs and digital signals will look like. Uh, an analog signal would have a continuous waveform, continuous, right? Whereas a digital signal would have that discrete uh, state where its values are going to be uh, limited to either a high or a low, or or on and off, or 1 or 0. So it's taking only discrete values in its representation. Whereas on the analog side, it would have a continuous wave or waveform, a continuous form with infinite range of numbers. Okay. So now let's take them one by one. Let's take analog and digital one by one and see what are some of the properties that we need to be looking at in terms of its representation on a given medium. Okay. So as usually they say, analog signals are more of a sine wave. So they would have which means they would have an amplitude that corresponds to a time frame. So here you'd have an amplitude of say uh, five either signal level, you know, and it just it moves like if you were to sketch a sine function, it just goes in a waveform. So hence the representation of analog having a sine wave form, or taking on a sine wave form, because when you do sketch sine, the function sine, this is kind of like the way it kind of graphs out, and it's more or less related to how analog signals are transmitted when they given medium. Okay, and depending on the amplitude, you could have depending on amplitude, you could have so depending on amplitude and time, you could have that form, that sine wave, either increasing in uh, its what you call it, its representation or its form or shape when it comes to the transmission. So if you look at this, for instance, we do have 5 as the level, as the peak level for this sine wave over here. If we're to increase the amplitude to maybe 10, then obviously it would more or less go up and increase its waveform. So the higher the amplitude means you're gonna have a lot more uh, uh, frequency oscillation or sine of oscillations back and forth. And the less the amplitude, the less the oscillation of the signal. So in this case, you do have 10. If you to increase it, you know the oscillation is much more higher. Within the same time given frame of just 1 second here. So you need a key difference. You have a lot more of uh, the the frequency representation, the frequency of the wave or the signal. Okay, so just keep that in mind. The more amplitude you have, the more frequency of the more the frequency of the wave increases, I guess. But the less the amplitude, the less the frequency of the wave. So you can see if you apply more power to the signal being transmitted, then you're bound to get a lot more oscillations or a lot more frequency representation of the signal. And the less power you have, then you do have less of it being transmitted. Um, but within some states, in some occasions as well, you should also look at the function that relates to the signal being transmitted. If there are other elements involved or there are time sequence involved in the signal representation, it could also affect how the oscillation or the repetitiveness of the frequency would occur, or the frequency wave would occur. So besides considering just the increment of the amplitude, or besides the variation of the amplitude, you also have to consider the some of the various factors that falls within the time frame of the signal being transmitted to determine whether the oscillation or the frequency of the signal would either be higher or less, will be more or less. Okay, so with this, if you notice the value that they were using when it was just when the when the frequency was 4, you did have at an amplitude of 5, it had not as much frequency as you would expect. But when we started increasing the amplitude as well as the frequency level, we saw a significant boost. But look at the last one, for instance. We went back to the 5 amplitude as well as, and then we decreased the frequency level and did put increased a bit of uh, this function over here to determine how wide the frequency oscillation to take shape. How wide would it take shape? So once we did apply that value, which is pi divided by 2 to your is that sine theta, whatever it is, the symbol here, you notice that the oscillation was much wider in terms of its durations. So it will take a longer time for even its frequency to complete to one repetition in its transmission. So there are a number of things that basically you need to consider when it comes to how sine waves uh, represent analog signals. A number of factors goes into play. It's even though the amplitude plays a key role, factors like the frequency level as well as this t-type can also change the way the wave or the frequency of the signal, so the signal wave would actually oscillate within a given transmission. Okay, bandwidth of a composite signal is the difference between the highest and then the lowest frequency contained within that particular signal. So, in a sense, if you want to look at bandwidth from an amplitude and frequency point of view, the composition of the signal and the difference between its highest peak and its lowest frequency or its lowest peak would determine the bandwidth capacity of that particular frequency transmission in a way what you term as a bandwidth. Okay, so bandwidth of a composite signal is the difference between the highest and the lowest frequency contained within the signal. So if you were to look at this bandwidth from this composite signal, for instance, then you could say that the bandwidth of this particular composite signal here would be the highest frequency level minus the lowest frequency level. So it'll be 5,000 minus 1,000, which will give you 4,000 hertz to represent the uh, bandwidth of this composite signal. Okay. Digital signal, on the other hand, um, in addition to it being represented by an analog signal, uh, information can be represented via digital forms. So we're looking at digital signals, and uh, it and since we know data can be represented either analog or digital, when digital forms takes effect for information or data being transmitted, representation at the digital level can either have two discrete states or discrete value in terms of its representation, and that can either be 1 or 0, as I've mentioned earlier on. So for example, when you do have a 1 can be encoded as a positive voltage, and a 0 uh, can be encoded as a 0 voltage. So in that sense, a digital signal can have uh, uh, more than two levels, especially if you're looking at it from a signaling point. Obviously, it would have various levels, but its representation is either uh, 0 or 1, even though it would have more of that levels. Okay, so if we were to send more than 1 bit for each level, then it would increase the number of uh, signal levels that we expect within the transmission at the digital level side. So yeah, that's what this is basically saying. It's just telling that in addition to uh, being represented by an analog signal, information can also be represented as digital or in a digital form. And for example, a 1 can be encoded as positive voltage, and a 0 can be 0 voltage. So when you do have a digital signal, taking taking either a 1 or a 0, within its signaling level, it can take up multiple levels, but the value wise in terms of its states can either be positive 1, or it can either be on and off. In this case you have 1 being encoded as a positive and 0 being a 0 voltage, looking at it from a voltage point of view. So looking at how digital signals are represented, um, we can try to look at how bit sequence for a given message could be represented if we go with the approach that 1 is encoded as a positive voltage and 0 as a 0 voltage, and it's having more levels depending on the number of bits being transmitted. So just let's look at it from that point of view and see what a typical digital signal will look like. So here you have a typical signal, digital signal. So here you do have your positive voltage for one and your zero voltage for zeros, and that just cuts across. So you do have high lows, high highs for the ones, lows for the zeros, highs for the ones. For this 8-bit 1, 2, 3, 4, 5, 6, 7, 8, for this 8-bit sequence. So if you look at it, you notice that in terms of uh, levels, the more bits we have, the more of the levels that we do have, that we do get. So the more bits, you get a lot more levels, so you do have uh, a high level, a low level, a high level, a low level, and a high levels. So the more the bits, the more the levels that you're going to be expecting within a digital signal. Now, within this, there needs to be a way to calculate how long some of these bits actually takes before the a transition between the various bits that uh, they account for that makes up that message. So, like for instance, in terms of time and amplitude computation, you want to know how long this bit takes before it transitions to the next bit. And usually the time it takes for the entire bit for a given message to be transmitted is what you term as the bit rate. The entire time taken for one message. So this is just one message over here. That's represented by 8-bit sequence. Okay, so the time it takes for all these bits to be registered in a digital signaling is what you term the bit rate. By the time it takes for one bit to transition to another bit, it's what you term as the bit interval. So the interval between bits is where one bit changes its form or shape, or sorry, it changes its state level if it's a different bit value. Okay, so in this case, the time for this one bit uh, to change its state to the next bit, which is zero, will be considered the bit duration. So there you go. So you do have the time it takes for this bit to transition or change each state based on the next bit that's in sequence will be considered the bit level, so the bit interval, and a bit rate is the time it takes for the entire bits to be transmitted. So in this case, for a 1 second period, 8 bits uh, uh, were transmitted. So in that case, we would have a bit rate of 8 bits per second, and they do have obviously um, 8-bit interval as well, because it's 1 second that represents that particular 8-bit sequence that we did have. Okay, so 1 second equals 8-bit intervals, which would then form the bit rate of 8 bits per second. So computational wise, if we wanted to put this into perspective in terms of calculations and all that, what have you, I want to look at some examples of how some of these calculations can be done when you do have a given information. Like for instance, you do have a digital signal that has a bit rate of 2